From everybody? You want credit, got to be up here now. And I hope you put your name on both sheets. It's 2 pieces of paper.
You got mine back. You got mine back. Can I get mine back so I can put my name on the second page?
$10. Come on up here, do it now.
If it's stapled together, does that work?
If your paper's stapled, okay, but still you should have your name on both sheets.
Nope.
I mean,
Very confusing, Dr. Horvath.
what is that?
It's very confusing.
Okay. Sorry. Wonderful. You give, please, the other stack to Lynn. All right, let's finish chapter 22 on electrochem. We said yesterday the last issue is on deriving E0 values for new half cells. You can develop all sorts of new half cells by appropriate combination of half cells which you see listed in table 2. The example given is for iron being oxidized in the presence of water to hydrated iron plus 2, put together with iron plus 2, hydrated iron plus 2, being oxidized to hydrated iron plus 3. Those two half cells appear in the table. The respective potentials are plus 0.44 volts for iron going to hydrated iron plus 2, and minus 0.77 volts for hydrated iron plus 2 going to hydrated iron plus 3. If we add those two half cells together as written, we get a new half cell which illustrates iron in the presence of water being oxidized to hydrated iron plus 3. The only reasonable decision we can make on the E0 value for that derived half cell is that it'll be someplace between plus 0.44 volts and minus 0.77 volts. But as we said, you can't couple half cell reactions to get a new half cell reaction, because the coupling process requires putting half cells together to get a net cell reaction in which there is no net electricity. But for any transformation, even for a half reaction, the changes in energy are always additive. So the way to do this is to go through change in energy, which means with the fundamental relationship delta G0 is minus NFE0, where F is the Faraday constant, 96,500 coulombs. You can calculate delta G0 for the reactions to get delta G0 for iron going to iron plus 3, hydrated iron plus 3. And then with delta G0 now available equal minus NFE0, where N is now 3, calculate E0 for this third remaining derived half reaction. Here's the arithmetic. We had this on the board yesterday, but just to be sure you've got this in total, we have rewritten it. Here's what we did. By Hess's law, we added half reaction 1 to half reaction 2. We got half reaction 3. For which, again, the question is, what's the E0 value? So here is where we have combined the standard changes in free energy for each of the component half reactions, this one and this one, which we can do because we've got the E0 values for each of these. And then here's the calculation to get E03. That is the method given by textbooks on electrochemistry to do this task. But frankly, I prefer this. I call it the better method. This shows how we can get the same information by using standard changes in free energies of formation from Table 1 as necessary. And this also shows how you can get standard changes in free energy of formation for species whose formulas are not contained in Table 1.
On the delta G over there, if it's equal to negative n Fe, is the negative, where does it go over in that equation?
I don't know what your question means.
Like, I think, is there a negative sign missing in that equation? If it's delta G of isn't it equal to negative n?
Can I leave out signs? Let me see here. Always arithmetic, never chemistry. I think I got the signs right. You work through the arithmetic. If you still got a problem after you work through the arithmetic, we'll talk about it. Now, back to this. If you look in Table 1, you will find out that delta G sub F super 0 for hydrated iron plus 2 as well as hydrated iron plus 3. Not contained in Table 1. How could we get this information? If indeed we're going to get at delta G, at E0 for this derived half reaction. Well, from 1, here's 1. Half reaction 1. If you look at Table 1, what's delta G sub F super 0 for this stuff? Without looking at the table. This kind of stuff is going to be on exam 3. What's delta G sub F super 0 for any element in its standard state? 0. No change in free energy in forming an element from itself. But I make a point of that because it's this stuff which seems to be obvious, at least to textbook authors, but often is not obvious to students. If you look at Table 1, for standard state element, you'll see a whole bunch of zeros in the delta G sub F super 0 column and the delta H sub F super 0 column. You won't see 0 in the entropy column because these are material objects. They have entropies. But remember, the entropy is an absolute value. It's not a delta value. There's no change in enthalpy in forming an element from itself. Or forming a mole of an element from itself, no change in free energy. Mole, remember, sub F means make a mole, okay? So when you go to this half reaction and examine table 1, the delta G sub F super zero information that you will need to get from table 1 is delta G sub F super zero for water liquid. This is 0. You got E0. Since you got E0 from this, you get the change in free energy for this reaction. Since the E0 value is plus, you know the change in free energy for this reaction is spon or non-spon? Plus or minus? What is it? Plus or minus? If E0 is plus, remember E0 is a measure of potential. Something which is spontaneous has a tendency to go, doesn't it? That means its tendency to go is positive, which means the change in free energy for this tendency to go is going to be what? Minus, because that corresponds to spontaneous, okay? So delta G0 for this thing is going to be minus. But again, since we got E0, we get delta G0 for the reaction. We apply Hess's law. I wrote it over here. You get delta G0 for the reaction, which is what we just talked about. Okay? From this. Here's the puzzle part we don't know. Here's the puzzle part we have available from table 1. So you do the arithmetic, you calculate delta G sub F super 0 for iron plus 2. So now we go to the second half reaction. That's this thing. We got the E0 value, so with this we can get the standard change in free energy. This E0 value is minus. So the standard change in free energy for this reaction corresponds to spon or non-spon. What is it? Non-spon. So that's going to have a positive sign on delta G0. But now, from 1, we got delta G sub F super 0 for this stuff. But again, in table 1, you will not find delta G sub F super 0 for this stuff. But now we can get it. So we go to 2. With the intention of calculating delta G sub F super 0 for hydrated iron plus 3. We get delta G0 for the reaction from this. From half reaction 1, we got delta G sub F super 0 for hydrated iron plus 2. So we calculate. This is the only unknown now. Delta G sub F super 0 for hydrated iron plus 3. So now when we go to the half reaction, which is the derived half reaction, this one. And we want to get the E0 value. Delta G sub F super 0, 0, standard state iron. 6 times delta G sub F super 0 for water liquid, with delta G sub F super 0 for water liquid coming from table 1. Delta G sub F super 0 for hydrated iron plus 3 we just got from half reaction number 2. So, the only thing we don't know is delta G0 for the reaction. So we get delta G0 for the reaction, because again, these changes in free energy are additive. And then with this, we compute E0. I did the arithmetic and find out that you get the same number. I'm not surprised that you get the same number, but I also wouldn't be surprised if you got a number that was close but not exactly the same. Because all the information you find in a data table like table 1, or E0 table like table 2 in chapter 22 on electrochem, this stuff all comes from measurements, and measurements made by different people. They don't always get exactly the same value. And oftentimes in the world of chemistry, time has not yet been taken to find out who made the measurements more carefully, whose data is better. So, what can you do? What I usually do is to look to see in National Bureau of Standards data, which is where Table 1 comes from, what the information is there. Because that's probably the most reliable. Because I should imagine the people who compile a data table for the National Bureau of Standards will have the intention of being as careful and precise with this information as they can be. But I have found data in Table 1, which I know is not right. It comes from measurements. One word of direction, a reminder. If you wish to study science, for whatever reason, always be skeptical. Always. Don't take anything on faith. Never. Not in science. Doesn't work. Always be skeptical. Always be doubting. Now that doesn't mean to be negatively doubting, like the word criticize. Somehow, some way, the word criticize has got bastardized in our language. People now believe that if you are criticized, that means somebody's saying something negative about you. No. That only means they're being skeptical. They're trying to find out for sure if what you have said is correct or reliable. Not necessarily negative. They're being critical of what you've said. That doesn't mean wrong. Doesn't mean you've done something wrong. Okay? And again, all these fundamental relationships are on the information sheet. I don't expect you to memorize any of this stuff. But I do expect you to know facts like delta G sub F super 0 for standard state elements are 0. If you have to deal with delta G sub F super 0 for molecular hydrogen gas, 0. Delta H 0 sub F. Delta H sub F super 0. 0. And that kind of stuff I expect you to know. So we go. Well, before we go to chapter 23, let's take a quick look at question 2234 on page 2229. You see a half reaction involving calcium metal. Where calcium metal is being oxidized in the presence of aqueous sulfate ion. It's really more likely to be this product, gypsum. But we can leave it at this for the conversation. You now know how to get at determination of E0 for this half reaction. Well, actually, I have that in here. From table 1, you will find delta G sub F super 0 for this. The conversation we just had reminds you that you have available delta G sub F super 0 for this. And in table 1, you'll also find delta G sub F super 0 for this, given that this is quite a common ion. So, you can get delta G0 for the reaction, and then with delta G0 equals minus NFE equals minus 2 times F times E0, not NFE but E0, NFE0. You can get E0 for the half reaction. Look at table 2, the half reactions in the chapter on electrochemistry. Where do you think this half reaction will fit? in Table 2. More specifically, do you see in Table 2 a half reaction involving the oxidation of calcium in the presence of hydroxide ion to make calcium hydroxide? You see that one, don't you? Plus 3.02 volts. Where do you think E0 for this thing? How do you, pardon me, not where, but how do you think E0 for this is going to compare to plus 3.02 volts?
It'll be pretty close to it.
Pretty close. I'll accept that. Why?
Their KSPs are pretty similar.
What is that?
Their KSPs are similar.
Say again?
Their KSPs are similar.
KSPs of what? You're on the right track. I just want you to be more specific.
Calcium sulfate and calcium hydroxide.
All right, now let's be a little bit more on the money. Which material is more stable in the presence of water? Is it calcium hydroxide or calcium sulfate?
Calcium sulfate.
More stable. A little bit less soluble. Right? So so how will E0 for this compare more rigorously to plus 3.02 volts?
A little less than 3.02.
A little what?
More than
A
3.02.
little more. Because this is a little bit more stable than calcium hydroxide, right? Remember, these E0s are tendencies to form. What if I put this in there? Where would E0 for this thing stack up? We talked about this stuff. Chapter 19. I think Mr. Mosen worked through this stuff with you, but whether or not he did, you in laboratory did this, didn't you? Regarding Chapter 19 in the notes on semi-soluble salt equilibrium systems, in laboratory, experiment 3, you pursued 3 methods to test for calcium ion in solution, didn't you? What were the 3 methods you pursued? Testing for calcium ion in water solution. Assignment 3, 46 laboratory. You tried to test for calcium ion by carbonate precipitation. What else did you do? Is this already ancient history? You've entombed it with your chemistry mummies? How about precipitation of calcium ion as the sulfate? How about precipitation of calcium ion as the hydroxide? This is stuff you did in lab. And you know me, you did it in lab, I expect you to know about it. That's it. Particularly because it relates directly to a lot of what we talked about in here. I don't know about the other 46 classes or 45 classes, but when I run this class, I want it to integrate with laboratory work as much as possible. That's where the hell chemistry is really done, in laboratory. And I jump up and down and holler at these. I said, what in the hell are you doing? You don't pay attention to what goes on in lab. How can you have this stuff ever sink in from an understanding standpoint? And I get all blah, 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 blah answers. I want to change the rules. I want every general chemistry student at this university to take general chemistry with me, period. No choice. You're either going to come away with some understanding or you're not going to cut the mustard. That's it. And I don't give a damn if you don't cut the mustard. I mean it. This stuff's important. You want to be a scientist? You want to be a physician? You need to understand. I mean it. When people come to me with A's from 2045 and they got no idea what I'm talking about, when I talk about what does electronegativity mean, how do I write Lewis structures for more complicated species? What the hell's going on here? Fundamental nomenclature. We don't know that. But you can calculate a spectrum, energy for a spectrum in the hydrogen, for a line in the hydrogen spectrum. I could care less. That's fundamental physics. Sure, it's important, but it's not chemistry, damn it. They say, you take time to do that stuff, then you're wasting time. You're losing time that should be used to talk about chemistry. This is chemistry class. I don't know what would happen if we adopted this rule. Rebellion. Chaos. Signs all over campus. Hang Horvath. So what? I don't care. I mean it. What I'm saying I don't care about is the consequence. I do care very much. I want you to learn. That's where it's at. You found with your work in assignment 346L that in neutral or basic solution, the most effective, simple way to test for calcium ion is carbonate precipitation, because it's much more stable, much less soluble than hydroxide or sulfate. But if you got an acidic solution, you got a problem regarding testing for calcium ion. What's the problem? You going to make calcium hydroxide in acidic solution? No. If you understood what went on in chapter 19 when you went through this with Mosen, you understood you can't make calcium carbonate at a pH less than 6. It's too acidic. Carbonates are too basic. So I'll ask a question. I ask a lot of questions. You're doing an unknown. You found out that the sample contains sodium ion by flame analysis, which means you can't get a calcium ion by flame analysis because the sodium ion flame is too intense. It masks the calcium flame. So if you want to find out if a solution of the sample contains calcium ion, you're now forced to go after it by precipitation. So the solution contains sodium ion. So flame test is out for calcium ion. And solution has pH on the order of 6.0. It's got ammonium ion in there, possibly. Okay? You have also discovered that the sample is a soluble sample. That means the sample itself is not calcium hydroxide or calcium sulfate or calcium carbonate, nor magnesium carbonate, nor magnesium hydroxide. What did I just do? I ran through the list of every possible salt when you do an assignment 5 analysis that would resist ready dissolving. That's it. Just those 5. Okay? And when you tackle assignment 5, you should know all that stuff before you start doing any investigation, because it all follows from the work you did in lab. So you got this solution. It can't be got at calcium ion by flame analysis because it's got sodium ion in it. Solution's got a pH of 6.0. You're at the reagent shelf. You see 0.5 molar sodium sulfate. And 0.5 molar sodium carbonate. Which of these solutions do you grab and start adding to the test solution to see if you got calcium ion?
Carbonate.
I got a vote for carbonate. Any other votes for carbonate? Another vote for carbonate. No. We got 5, 6, 7, 8. Oh my. Maybe you learned about this stuff. I hope you did. Could I succeed? Could I be successful in testing for the presence of calcium ion by using this solution? Absolutely. But calcium carbonate is less soluble. But keep in mind, you're not going to get calcium carbonate at a pH of 6. Remember, the solution is a pH of 6. Are you still going to use this solution? Don't let me talk you out of this.
Yeah.
Because I'm still going to use this solution. Do you think this solution that you have made of your unknown is a buffer? You think it's a buffer? If it's a buffer, you got a problem. That's going to try to stay at this pH, which means as you add carbonate ion, the carbonate ion will get killed. But do you think that solution of your unknown sample is a buffer? No, I don't think it's a buffer. I got no cause to think it's a buffer. So I'm going to use this. Because as soon as I put this in there, the pH of this solution is going to start doing what? Go up. And as soon as I make this pH go up, and it doesn't have to go up a whole lot, calcium carbonate becomes easier to form than calcium sulfate. Plus, you should have also learned with the work you did in assignment 3 that calcium sulfate forms a little bit slowly. But as you know, right, calcium sulfate is certainly precipitatable in acid solution because you made calcium sulfate in assignment 3 by doing what? Anybody remember how you made calcium sulfate?
Centrifugation.
That's not a way to make calcium sulfate. Heat what?
Calcium sulfate solution.
I said first you got to make it. How do you make calcium sulfate?
Acidify the solution of calcium ion.
Well, what solution of calcium ion?
Soluble solution.
I'm going to put you in lab right now, and here's the job. Everybody has to make calcium sulfate. And that doesn't mean go to the side shelf and find a bottle that says calcium sulfate on it. That's not making the damn stuff, it's buying it. What will you do to make calcium sulfate? You put together a solution with calcium ion in it and a solution with sulfate ion in it, right? Nothing fancy about that. But that's not the way you made it in lab. You made it in lab in a fashion which demands your recognition that calcium sulfate is readily formable in a very strongly acidic solution. Because to make calcium sulfate in 46 laboratory assignment 3, you mixed half molar calcium chloride solution, here's your calcium ion source, with 3 molar sulfuric acid solution. Is this solution fairly acidic? You're damn right. But that's how you make calcium sulfate. So this is screaming at you. Calcium sulfate is certainly formable in a strongly acidic solution. Hey, that's strongly acidic. Right?
If the pH was lower, like 2, 3, would you still use the carbonate and just count on the pH going up, or would you use the sulfate?
It's a judgment call. I can go at it either way. But I even purposely put an experiment in assignment 3 for you folks to try to protect you from missing calcium ion in a sample. You remember the little experiment near the end of assignment 3 where I said, put together calcium ion with sulfate ion and be sure to watch the system as precipitation develops so that you will see this is a somewhat slow process, somewhat time dependent, as opposed to putting together calcium ion with carbonate ion, because as soon as you put calcium ion together with carbonate ion in solution, bam! There's the calcium carbonate, just like that. That's why you get little tiny powder. Little tiny particles of powder. When you make calcium sulfate, you'll get more crystalline, definitely crystalline stuff. Because the slower the lattice develops, the larger are the crystal components of the lattice. Right. You get stuff like this in an organic lab. Crystallization and recrystallization is a method commonly used in organic lab for preparation and purification of material. Well, interesting stuff, okay? So, the point of this is to realize, I can test for calcium ion with this, but calcium sulfate does not form nearly as readily as calcium carbonate. Just be aware of such. But I know what students do oftentimes when they're doing unknown analysis. They're in a hurry. The most common complaint I get regarding 46 laboratory is, you don't give me enough time for unknowns. Baloney. I've given you 3 times the amount of time you need if you know what you're doing. And if you don't know what you're doing, I can give you all week. Who cares? I see students doing test after test after test which do not need to be done because they don't know the chemistry. That's not what we want. You can do any one of these unknown analyses, both samples in 30 minutes easily, if you know what's going on. If you don't know what's going on, well, you go on and on and on and on and on and on and on. Well, in any case, enough of that sermon. Let's go to chapter 23. First, look at this reminder. Homework. To get started successfully in understanding what I need you to understand in chapter 23, you have to understand periodic size trends. Now, my bet is you did some of this in 2045. Maybe you did it fairly thoroughly. I hope you did. Let's do it this way. This is left to right across a period. This is bottom to top, going up a family. When you read chapter 23 in the notes, the first few pages are all about stuff you should have got in 45. But I want to be sure, so I put it there. Because you talked about size trends and things like that in 45. And you recognized that for A families, not B families. You know, A families, the tall vertical columns, not the transition metal elements. From the bottom of an A family to the top of an A family, what is the size trend that you observed? Atoms get smaller from bottom to top. And as you go from period to period, like for example, a lithium atom versus a sodium atom, there's a big difference in size. And what the information in this video will tell you about, which again is presumably stuff you heard about in 2045, because I think the 2045 folks do pay attention to this, is when you go to lithium versus sodium, for example, the defining feature, the distinguishing feature of these two atoms is a 2s1 valence config for lithium versus a 3s1 valence config for sodium. So it's this single 2s electron which really defines the size of a lithium atom, and the single 3s electron which defines the size of a sodium atom. Okay? Now, along with this, you looked at radial probability graphs. I'm betting Radial probability is this way, distance from nucleus and this is really radial probability this way. How many of you have heard this term? Radial probability. You heard it. What's it mean? We don't know what it means. All right? Let's take an atom. Potassium. Okay? Consider K. Total configuration for K. Argon core, that accounts for 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. Boom. All done by writing argon wrapped up in brackets. And 4s1. If I consider radial probability for argon, potassium, pardon me, what I'm doing is imagining that I'm standing at the nucleus of a potassium atom. We are at the nucleus of a potassium atom. Now, our general model of an atom is to take it as a sphere. Okay? So it doesn't make any difference when I'm at the center of this sphere which direction I look, since a sphere is perfectly symmetrical about its nucleus. Okay? So I'm going to stand at this nucleus of the K atom, and I'm going to look in a direction. I don't care what direction. And I'm going to see all the electrons of which the electron configuration of this atom is composed. So I'm going to see 2 1s electrons, 2 2s electrons. I got really good eyes. I know if these are s electrons, p electrons, all that. You are charged with the same property. You are at the nucleus of the potassium atom. You are looking out at a given direction. So along with me, you are there. You're seeing 2 1s electrons, 2 2s electrons, 6 2p electrons, 2 3s electrons, 6 3p electrons, and then finally you see the 4s electron. All right? And you also learned in 2045. Take, for example, the simplest atom, hydrogen. As you stand at the nucleus of hydrogen and see only one electron, the electron has 2 perspectives, doesn't it? What are the 2 perspectives that an electron has? It's a particle, isn't it? Is it just a particle? What is it beside a particle? It's a wave! That's why that dirty damned electron can be at a whole bunch of different places at the same time. How about that? That's what makes these electrons really tough to grapple with. According to the Heisenberg principle, there's no way in the universe, no matter how hard we try, how hard we think, and no matter how clever are the experiments we design, we can never know exactly what an electron is. Never. I think that's wonderful. The little electron is far smarter than all our brilliant scientists and computers and all that stuff. I think that's cute. Yay for the electron. Outfoxes everybody. Okay? So when I look from the nucleus, in this case of the hydrogen atom, I don't just see a particle, I see this wave, which has simultaneous existence at a whole bunch of different places. But where do I see the electron most often? Let's imagine I'm looking in this direction. My eyeballs are at the center of the hydrogen atom. Okay? Each time I look this way, Actually, what I'm going to do is not that. I'm going to do this. I'm going to blink. The only time I can see the electron is when I unblink. Okay? I got my eyes open. Am I going to see that electron, even behaving as a particle, in exactly the same distance from the nucleus all the time? No, I'm not. But I'm going to see it at the Bohr radius. Remember the Bohr radius? That's the most common distance the electron for the hydrogen atom shows from its nucleus, which is what defines the size of the hydrogen atom. The most common distance from the nucleus for the electron of the hydrogen atom is called the Bohr radius. It's 0.52 angstroms. I don't care about the data point. But because this thing is also a wave, we can't say exactly where it is. So we'll use a probability function to describe where it is. The probability, here's the nucleus right here. Is the electron ever in the nucleus? No, because then the atom would disappear. As I get further and further from the nucleus, the probability of finding the electron becomes ever increasingly small. But does this part of my probability curve ever touch this axis? Do I ever get zero probability of finding an electron? No. If I got a hydrogen atom in my tweezers right here, there is a minuscule probability that I can find its electron in Newberry. Don't bet on it, because the odds against it are so huge it would make Avogadro's number look like nothing. But it's still not zero. So what I've drawn here is radial probability for a 1s electron. And this distance corresponds to this distance from the nucleus right here. See? Where I'm at the peak of this probability function. This is called MPD, most probable distance, which for the hydrogen atom is the Bohr radius. This is what corresponds to the size, the observed size of the hydrogen atom. Again, if my memory's right, it's 0.52 angstroms. I don't care about that. Okay? So, what I'm getting at is, when I'm looking now from the nucleus of my potassium atom and I'm seeing all these different kinds of electrons, I'm going to see a whole bunch of different probability functions, all overlapped on each other. I'm going to see the probability function for 1s electron, and I'm going to see the probability function for 2s, which will be like this. You see this little blip in here? This is for 2s. Put 2s in there. Do you remember in 2045 when you took an atom, not an atom, but an orbital, a 2s orbital, okay? And you chopped the 2s orbital in half. Given that all s orbitals are essentially spherical, what did you see when you took a 2s orbital and sawed it in half? Here, x, y, z Cartesian coordinate axes. X, I'm going to put z up here because that's the way chemists do it. What's this picture I just drew? If we're talking about orbitals, what would this picture correspond to? What is it? A 1s orbital. And if I'm talking about an atom like lithium, which has got a 2s valence electron, then I'm going to be concerned with a 2s orbital. Because after I go from 1s, the next orbital I find is 2s. All right? So here's a 2s orbital. And the boundary surface of this 2s orbital, for the case we're presently discussing, corresponds to the observed radius of the lithium atom. Okay? But I'm going to now take this 2s orbital, I'm going to saw it in half. What am I going to see when I saw this thing in half? Am I going to see a uniform electron density cloud? What will I see? Or put it this way. Do you remember the word node? What's node mean?
A focal point?
A what?
A focal point?
A what kind of point?
Focal?
Focal point.
It's a point where no electrons can exist.
Well, talk to me about a node in terms of probability.
The probability is so low that it can't.
How low?
Really?
What's the lowest probability you can find?
0?
Yeah, how about that? Okay? You see this here? This little hump and this big hump correspond to radial probability for a 2s electron. Okay? The little hump and the big hump. Because a 2s electron on a time average basis can be found real close to the nucleus. Even closer than the 1s electron. How about that? But most likely you'll find the 2s electron much further from the nucleus than the 1s electron. And if I take this and saw it in half, I see a boundary surface here. His boundary surface is a node. So here is, to me, where the mystery of the electron is first revealed, its wave character. Because what we're seeing is when we take this 2s orbital and chop it in half, we're finding out at any given instant, not different times, at the same instant, the 2s electron is here because it has a non-zero probability of being found here. And it's here, and more likely here. That's why the probability is much higher finding the 2s electron here than it is here. That's why this part of my probability graph for 2s is much greater, much larger than this part. But it's never here. That's a node. So there's that wonderful electron. It occupies this whole region. It's more likely here, but it's also here, but it's never there. I like this electron. It's all this in all this territory at the same time, but more likely here and sometimes here, but never here at this node. Isn't that neat? One electron doing all this kind of stuff. Well, at the minimum, I think we have to admit, we cannot concoct a physical picture of this electron. Oh, can we? How could we see something which is all this at the same time, yet but never in this it's this wave stuff, okay? So that's what we're doing with this probability stuff. 2s. Then when we get to 2p, the 2p looks like this. So this is interesting. Because what we're seeing here, I mean, the graph is getting messy and messy. Because the more probability parts I put on the graph, the more messy the graph gets. So this is MPD 1s. Here is MPD 2p. And here, right here, that's MPD 2s. So, with this before us, let's ask a question. How do you think these two atoms compare size-wise? Now, you know the answer because you remember these size trends, didn't you? As we go left to right across the period, what do you see size trend-wise? Left to right across the period. Atoms get progressively smaller, but not substantially or significantly so in most cases as you go from atom to next atom. Okay? But if I look at lithium versus neon, now I moved through 8 atoms. And by the time I go from lithium to neon, there's a big difference in size. Neon's a lot smaller than lithium. But neon not a whole lot smaller than fluorine, and fluorine not a whole lot smaller than oxygen. It's just that I'm adding up a whole bunch of small differences in size. In time I go from lithium to neon, big difference in size. So when I look at lithium, beryllium, I know size trend-wise, this atom is a little bit smaller. Okay? Now let's talk about first ionization energy. Or IE1. That's first ionization energy. We're talking about lithium becoming lithium plus and beryllium becoming beryllium plus. All right? How do the first ionization energies of these two atoms compare? Or at least how do you expect them to compare? Which one of these is harder to take an electron away from? Lithium or beryllium? One or the other?
Beryllium.
Beryllium. Are we surprised? Because when I ionize lithium, I'm taking away a 2s electron. When I ionize beryllium, I'm taking away a 2s electron. I'm taking away the same kind of electron. But notice that when I ionize beryllium, I'm taking away a 2s electron from an atom that's got how many protons? How many? 4. This one's only got 3. And I'm taking away the same kind of electron. So if I look at this radial probability graph, which already looks like hell because you got so many different parts to it, if this is the radial probability graph for lithium, and I want to redraw this and I want it to be the radial probability graph for beryllium, will this graph look exactly the same? How will it change? If this is for lithium, how will this graph change if I want to make the same graph for beryllium?
Smaller. No.
The answer lies in these MPDs. How will the MPDs change if I make this graph for beryllium? Will they stay the same, move further away, or come closer to the nucleus?
Come closer to
Come closer to the nucleus because beryllium, I got more protons. Okay? Pulling on the same kinds of electrons. Right? Lithium got a 1s2 core, beryllium got a 1s2 core. Lithium got a 2s1 valence electron, beryllium's got 2s valence electrons. So I know first ionization energy this, bigger than first ionization energy this, which keeps with the size trend. This smaller, more protons in the nucleus, harder to ionize. Okay? Now let's have fun. Boron. What do I find when I get to boron? I find the first atom in the periodic system which has an electron that's part of its configuration that is not an s electron. What is the configuration for boron? 1s2 core, 2s2, so far just like beryllium, and then 2p1. So we'll just write the valence part. Okay? And notice when I drew this, I showed you MPD2P is closer to the nucleus than MPD2S. Closer to the nucleus. And when I go from beryllium to boron, one more proton in the nucleus. Well, if MPD2P is closer, shorter distance from the nucleus than MPD2S, and boron's got 5 protons in the nucleus versus beryllium only 4 protons in the nucleus, which of these atoms is larger? Which one is larger? Beryllium is larger. Be larger than boron. Okay, so far? Now comes the fun question. Which one is harder to ionize? Beryllium's harder to ionize. Why is that?
It takes more energy to relieve the 2s2 than the 2p1.
Why?
Because
The answer's over here.
closer to the nucleus.
Wait a minute. MPD2P is shorter than MPD2S. On a time average basis, the 2s electron is farther from the nucleus than the 2p electron. So why the heck is boron easier to ionize than beryllium? The answer lies here. You see this little hump? This little hump is not part of the radial probability for 2p. It's only part of the radial probability for 2s. You'll see this stuff when you look at these probability graphs in chapter 23, which I want you to look at. Point. B, easier to ionize than Be, because B loses 2p electrons, whereas Be loses 2s electron. And losing the 2s electron is more difficult than losing the 2p electron because of this business. Penetration region for 2s, which is not part of the properties or probability for the 2p electron. Now, with that having been said, you read through chapter 23, covering this stuff on radial probability, and you look at this video. Because in this video, I delivered what I thought was a pretty good lecture on the stuff which we just more or less went over. And we'll pick it up from this point tomorrow. With the main intention being in 23, to establish a basis for rationalizing strengths of Bronsted-Lowry acids and bases. Very much a part of which is atomic size. That's why we're paying attention to this size stuff.